Hi everyone, my name is James Megariotis and I'm a mechanical engineering student at Drexel University. And I'm going to tell you a little bit about my 3D printed inverted pendulum robot project.
So first, I'm going to tell you a little bit about the design and construction of this robot. The robot is driven by two DC gear motors with quadrature encoders. Both motors run at 12 volts. To drive these motors, one Sabertooth dual 12-amp motor driver was employed. The control systems were implemented on an Arduino Mega 2560. Orientation data was gathered from an Adafruit BNO055 IMU. And for power, I used a Turnigy 5000 mAh lithium polymer battery pack. This is a 12-volt battery pack. All other components were custom designed and fabricated using Creo parametric 3D modeling software and a FlashForge Creator Pro 3D printer. All controller design and coding was done in Simulink and Matlab 2015B. As you can see here, I have provided time-lapse footage of the fabrication process of the robot components. The first component is the base in which the motors will be mounted. The second video shows the fabrication process of an extension. Two of these extensions were employed in order to house additional hardware and also raise the center of gravity of the robot for more stable operation. Here you can see a few pictures of the robot, with and without hardware affixed. The first challenge was to model the system and implement a controller that can stabilize the inverted pendulum robot. Here you can see a state space model of the system where the voltage applied is the input. All constants were either measured experimentally or calculated. These constants include moment of inertia and the torque and back EMF constants of the motor. In order to implement this controller, a Matlab script was designed to convert a continuous time state space model to a discrete time state space model that could be used for implementation on a microcontroller such as the Arduino. This script also calculated the optimal gain matrix for a linear quadratic state feedback regulator. The system is now stable, which is clearly indicated by the new pole placement. The following plot shows the performance and response of the system due to an initial pendulum angle of 0.2 radians. As you can see, the system quickly stabilizes. The next step was to design systems in Simulink that can acquire sensor data through the Arduino. These few blocks serve as the basis for my design environment and allow for the approximation of the state of the system in real time. This Simulink model was deployed as a standalone module on the Arduino. The IMU block acquires absolute orientation and gyroscope data in real time. The motor driver block converts a voltage between 12 and negative 12 volts to a pulse width modulation signal. And the read quadrature encoder block allows for the tracking of position and velocity of the individual motors. The IMU block first initializes the sensors and then begins acquiring quaternion and gyroscope data. The quaternions are then converted into Euler angles. The motor driver block consists of a subsystem for each individual motor. As you can see, the voltage between 12 and negative 12 volts is converted into a pulse width modulation signal compatible with the motor driver. The read quadrature encoder block was programmed using the Simulink S function builder. It was programmed in C. The read quadrature encoder block passes encoder tick counts to the wheel states block. These encoder ticks are then converted into rotational displacement and velocity, and then linear displacement and velocity. The state estimate subsystem averages the position and velocity and offsets any angle measurements. Lastly, the speed correction blocks were implemented in order to help the motors match speeds. As you will see from the first demonstration video, the speeds of the motors do not match, and the inverted pendulum robot begins to rotate about the right wheel. This video clearly shows that the linear quadratic regulator stabilizes the pendulum in both position and tilt angle, but has absolutely no control over the rotation of the robot. It can be seen in the next video that the implementation of the speed correction block helps to stabilize the rotation of the pendulum. While it still rotates, it rotates at a much slower rate while it attempts to match the speed of both motors. Further calibration is required in order to get a perfectly stable pendulum with no rotation about the right wheel. My plans for future research include expanding the state space model to include both heading and yaw rate to control the turning of the pendulum and also the rate at which it turns. I also plan to implement a computer vision based navigation system using the Matlab computer vision toolbox. All in all, Matlab and Simulink proved to be powerful tools in the design and implementation of my controller solution. I hope you have enjoyed my submission to the Matlab and Simulink low-cost hardware challenge. Thank you for watching.